All right, we're going to move on to irreducible quadratic factors, and we are going to sort of combine the irreducible quadratic factors and talk simultaneously about the singular cases and the cases where it's repeated. So the main thing that's very different is if you have an irreducible quadratic in your denominator, again, repeating the introduction video, irreducible quadratic means that if you were to graph the quadratic, it doesn't cross the x-axis. Equivalently, if you set it equal to 0, there are no real solutions. Equivalently, it has two complex conjugate solutions. So you can't factor it using only real numbers. You can't solve it using only real numbers. It has complex roots. So if that's the case for the quadratic in the bottom, then instead of putting just an a in the numerator, you put an ax plus b. Put an ax plus b. Okay. The idea is we want to use a degree less than what we have. So if it's an irreducible quadratic, then it may have a linear term in the top. Okay. So let's go through that and list off these partial fraction general forms. So for 1 over x squared plus 25, x squared plus 25 is an irreducible quadratic. So it looks like we have a linear and an irreducible quadratic. So the linear term contributes a over x, and then the irreducible quadratic term contributes a factor of the form bx plus c. Okay? So for the second one, we've got 25 over x times x squared plus 2x plus 5 squared. So now, whenever you have something written in the format x squared plus something squared, let's say little a, this is always irreducible. But you may have a quadratic that's written in this format here. Maybe I'll use a different thing. I'll just say maybe this is some k squared. I don't know, something different. So if you have something like this, you would actually have to take a look at the discriminant. Need to check. So in this case, I'll just take a look at the discriminant, which is b squared minus 4ac. So here, the a value is 1, the b value is 2, and the c value is 5. So the discriminant here is b squared, so 4, minus 4 times 1 times 5. So 4 minus 20, which is definitely negative. So this is irreducible. Complex solutions. Okay. So when in doubt, check. So here, we still have a linear factor that contributes a term of the form a over x. Plus, now we've got a repeated irreducible quadratic. So we follow the same scheme as the repeated linear factors. So we start with the factor itself, but then we keep adding terms until we make it to that power. So in this case, it's repeated 2 times. The multiplicity is 2. So we'd keep going until we get raised to the second power. Here we'd have bx plus c, and here we would have dx plus e. Okay, so moving on, we've got x minus 1 squared, which is a repeated linear factor, and x squared plus 9 is a irreducible quadratic. So the repeated linear factor will contribute a total of 2 terms, like that. The irreducible quadratic will contribute another single term, but in the numerator, instead of it being just an arbitrary constant, it is an arbitrary first-degree polynomial, which is a line, and a generic line is cx plus d. So this would be x squared plus 9 in the bottom for that irreducible quadratic. Okay, very similar down here, except for we now have our linear factor is no longer repeated. So we're going to have an x plus 1, and now we've got a repeated irreducible quadratic. So the linear factor will just give us a contribution of a single term now, but the irreducible quadratic will give us a contribution of 2 terms. So you always start with the factor itself, and then increase the power on it until you reach the power that's present in the problem. And then, of course, every time you have an irreducible quadratic, the form of the numerator is a bx plus c, or a generic line, or a generic first-degree polynomial. Lastly, we've got something written that's not clear from just viewing it. It's not clear if this is an irreducible quadratic or if it is just a quadratic that needs to be factored further. So let's take a look at our discriminant. So b squared minus 4ac. So this is 4 minus 12. That's less than 0. So this is irreducible. So this is an irreducible quadratic, and it's repeated with multiplicity 3. So this will actually contribute 3 terms. So we're going to have our, each one gets a generic line, so ax plus b, cx plus d, ex plus f. And then here we start with our factor, and then we keep increasing the power on it until we reach the power that's present in the problem. So third power. There we go. All right. Let's take a look at this next example, example 6, what to do when we have, actually, you know what, we'll make this its own video.